Welcome to Study Loop.
Here we're going to work out an example of conservation of energy. Okay, so conservation of energy says that your initial kinetic plus your initial potential is equal to the final values added together. So that's conservation of energy. But what we also need here is the idea of electric potential energy, that an electron moving in the field of two nearby point charges will experience an electrical potential energy from each of those in the amount k, q1, q2 over distance. And since there are multiple charges, we do have to add up the individual contributions from each individual particle. Okay, so we're going to let this electron start from rest in the middle between a positive 3 nanocoulomb charge and a positive 2. We'll put the positive 3 at the origin. And there is no initial kinetic energy. So what I'll be doing, and we want to find the final velocity when the electron goes from the middle directly between the two charges to a point 10 centimeters to the right of the 3 nanocoulomb charge, or to the right of the origin. So let's calculate the electric potential energies by themselves. The initial electric potential energy is going to have two terms to it. And there will be the electrical constant times the charge on the electron, and then first the 3 nanocoulomb charge over that distance, which is 25 centimeters or 0.25 meters. And then there will be a similar term for the second charge of 2 nanocoulombs. Okay, and we can use the standard values that the K is 8.99 times 10 to the ninth in SI units. And here I'm going to see that the 10 to the ninth will cancel the nanocoulombs. So I'm going to make things a little bit easier here. And then we've got 3 over 0.25 plus 2 over 0.25. And there may be easier ways to write that. And the whole value should be negative because an electron is negative. By the way, a negative potential energy really indicates a bound system. That little electron is getting attracted to both of the positive charges, and it will be somehow stuck. Maybe not. It'll probably just bang into the 3 nanocoulomb charge, and that's the end of it. Okay, so our initial potential energy winds up to be, let's see, minus 2.88 times 10 to the minus 17th joules. And we can do, likewise, a similar thing with the final. There will be 2 charges. We'll keep the same constants we did before, but the 2 charges that are attracting the electron will now have a different distance. The electron is 10 centimeters away from the 3 nanocoulomb and 40 centimeters from the 2. So we should have a more negative number. If we don't, we're doing something wrong. And time to rethink. And yes, we do get a lower potential energy to end with, which means that some of the energy got converted to kinetic. So let's put this together and then we can solve for the unknown velocity of the electron. So here is our beginning potential energy. Final potential energy is on the opposite side with the final quantities, and we have 1/2 m velocity final squared, speed squared final for the electron. And kind of working this out, I don't want to show too many of the intermediate steps, but what I finally wind up with is the V final squared is equal to 4.72 times 10 to the 13th. And that should be in meters per second squared. We won't worry too much. We've been using SI units. So taking a square root, we wind up with a fairly high speed. So yeah, electrons do move fairly quickly. Let's see. Let me check my numbers one more time. 6.87, beg your pardon. I thought that looked a little funny. There we go.